Okay, so today what I want to do is show you guys a little bit of how kinetics can be put into the context of some of the research that I do. And, you know, my research is only a small part of what can be done with kinetics, but I want to give a little bit of a perspective. And secondly, I want to start a new topic that we should be starting today, which is vibrations. And then vibrations is something that I also study in my research. Now, I said that I was going to do problem 4, problem 5C9. I did put a video that is different from the example video. Did anybody watch it? That talks about example 5C9. So please go and watch my video and then watch the solution, which is, so in my video I don't solve the problem, I just kind of talk about how to approach it in general. And I think that's a good way of thinking about these problems. In particular, the problem, it's the combined use of linear impulse momentum and work energy, right? So watch my video and then watch also the example video, which is not, you have to go to example videos link. It's not, actually I should show it here, sorry. So let me show it with, okay, for some reason. Okay, it's here. It's here. Share. So what I'm talking about is this. What I'm talking about is this example, right? 5C9. This is the setup of how to use these two tools together. And then for the solution, you can go and watch Professor Rhodes' solution is the same as what I would do. You go here, okay? So it's not the same link. I really highly encourage you to watch it. Again, highly encourage everybody to watch animations. It's a good way of visualizing what's going on. Very important. Okay. So let me first do vibrations. I'll set you up with what you need to learn to do the homework. But also, you know, those of you who have spoken with me one-to-one, I always say that, and I've said it here many times, that I don't really want you to be utilitarian in the sense I learn, lecture, I do homework, I do well in exams. I hope that what you learn here is going to serve you well for all, you know, for your life. And I said that it will if you learn it, and you will use it, you'll find ways to use it. So this, the reason I want to say that is because for the exam, I really encourage you to go and over the discussion sections. I've said this many times, but don't prepare for the exam only by doing previous exams and by looking at your homework. This is not an efficient way of learning and studying. One of the things that I showed you, and I hope that that I showed you, and I hope that you can do for actually, I think it's very effective learning, is to summarize what is being taught. So I think I didn't show this in class, but I want to show it before we go into vibrations. It's the Kinetics Table. I mean, I've shown it, and I told you that it's a good tool to remember. I can send this to you, or you can watch the video later. So maybe it's better if you just, you know, pay attention to what I'm going to do. What this is showing here is the summary of chapters 4 and 5. That's that. Now, what is extremely interesting to notice, and I hope some of you will go and figure and see what I'm talking about, is that if you think about Newton's second law, which is here, everything is coming from it. This is the same as this, right? We're just saying, okay, a rigid body, now I can say all its translation, it's captured by what the center of gravity is doing, right? So then I look at the acceleration of g. And then if I say, okay, what happens if I impose that all particles on a rigid body are keeping their distance fixed? That is what the rigid body is defined. If I apply that, Newton's second law under those conditions, I get Euler's equation. That is what we did in the last part of chapter 4D. But it's Newton's equation. We're not learning a new equation. If we go and take Newton's equation and we integrate it, acceleration is dv dt, right? If we write this as dv ds dt, we're only using chain rule. Then we can write Newton's equation in this way. M times, sorry, not dt, ds, m times, what is what is ds dt? You remember? Speed, right? Thanks. V dv. Okay? And if you integrate this side, which you can, it's only dependent on the, oops. Sorry, yes, I need this. If you integrate this side, then you get what is that quantity? Kinetic energy. So Newton's second law is the work energy equation. Because on this side, what you have is the integral of force times ds. What is ds? Infinitesimal displacement. If I integrate the displacement, I get the full displacement times a force. What is displacement times force? Work, right? So then you say, okay, in my sum of forces, I have some conservative forces. And we said that conservative forces are, or let's say, conservative forces times displacements do what? They do work, but they are potential energy, okay? And non-conservative forces times displacement is non-conservative work. So Newton's second law is the work energy equation, just transform. And if we do this and we integrate it, what do we get? We get linear impulse momentum. Do you see? You're just saying, oh, we can't see the screen. Oh, great. Sorry, chat. We integrate Newton's second law, acceleration first. I say acceleration is this. I send the dt here, and I integrate. dv integral of dv is d in two states. Right? I get linear impulse momentum equation. So it's the same equation. And if I integrate this guy for a rigid body, I get this. Yes? We did this in class. If I integrate this guy, and I say, actually, I don't have a rigid body, I just have a particle, I get this. It's the angular momentum of a particle, right? If you integrate the acceleration, you get velocity, and on the other side, you have your dt. So, what am I trying to show you with this? I'm trying to show you that this class and everything in mechanics comes from Newton's second law. I've said it many times, but I want you to visualize it. If you visualize it, maybe you convince yourself that it's not a lot of content. It's actually same content that you use in different ways. Now, if you go and read the discussion sections, you're going to visualize better how this Newton's second law gets these different schemes. But it's the same. It's just application of it in a different way. So look for these fundamental principles whenever you're studying, be it mechanics, be it thermodynamics, because these fundamental principles, everything is derived from it. Develop the ability to derive, even if we don't ask you in homework to do that. That ability to derive is what allows you to learn the fundamentals and apply them in many different ways. And this is very hard to get from doing problems and problems and problems. It's very hard, and it's good that it's hard. So otherwise, I've said that we would be automated out of jobs, right? If you can just, give a lot of examples to some AI algorithm, and engineers won't have jobs. But as you know, engineers are in short supply because it's hard to do these derivations. But you all are capable. You just need to get into the mindset of doing it. And then you'll find that life becomes far easier. Okay, so let me give you context, because of course we're learning, and it takes time to develop this. Now, first, everything comes from Newton's second law. This is very important. So it's not that you have really 4 tools. It's the same tool that can morph in different ways. How do I know which of the tools I use? Well, then I write here this output variable and this solution strategy. So if in a problem I'm asked to find accelerations, then I have to use Newton's second law, right? If it's a particle, then it's just this one. If it's a rigid body, I need to remember that there are going to be rotations, right? Forces and accelerations are vectors. So we need to be careful. We need to, understand that these quantities have different directions and that we are projecting them in different coordinates. What is the solution strategy? Well, I need to break up my system, and the reason I need to break up my system is because I need to find the moments and forces for each particle and each rigid body, okay? Now, this is a summary of chapters 4A and 5A. If you know that, you know everything. Well, there are a few other things, right? But like details like, okay, I need to keep the same point, etc. But if you know the concepts, you will be able to get that, grasp that easily. Now for work energy. For work energy, here what quantities do you have? Well, I have changes in position, changes in speed, changes in angular speed, and non-conservative work. This is what you can output from using work energy. Work energy is a scalar. You see, this conversion that I do there, it takes a vector and it converts it in a scalar because I'm taking all the movement into this arc length, right? So I'm taking this trajectory and I'm putting a coordinate that is curving along the trajectory of my system. That's why I make a scalar out of Newton's second law. And why? We have rotational energy, so we need to remember that when we have a rigid body. Now, what is my solution strategy when I look at my free body diagrams? Well, I take a system as a whole. Why do you think you have to break up the system for Newton-Euler when you have to look at the system as a whole for work energy? Intuitively, does anybody have, and you can make a wager, it doesn't matter if we're just learning here. Yes? Yeah, the right word there is concern. Anybody wants to make a statement about why? Why is it? Yes. Okay. Why do you look at the system as a whole? Yes? That is correct. So there are three things. In Newton order, we cannot forget two forces, conservation principles, and internal forces kind of don't do any meaningful work in a way. That's what you're saying. So can we summarize this on something? Okay, I will tell you. You look at the system as a whole because energy is conserved, right? Because internal forces cancel out in terms of work, which doesn't happen, of course, if you're looking at acceleration. Everybody needs to have their own force. So we create this control volume, this big system, and then you look at what's coming in and what's coming out and what's inside. And that's why you look at the system as a whole, because of the conservation possibility or the conservation property of energy. As a whole system, energy is conserved. Now, of course, there are dissipative forces that can cause non-conservation, and then we know that if they are present, we know that they are going to be dissipated. So if they don't remain in this big bubble, but otherwise the big bubble is because of that, because energy is conserved otherwise. And the same can be the same reason happens with linear impulse momentum and angular impulse momentum. We look at the system as a whole because conservation principle. And that's what you do your budget in and out. When you can conserve things, you can only look at what enters and what's leaving, and then you say whatever is inside needs to be conserved. So this is why conservation is so important, and we hammer it in thermodynamics, in here, everywhere. So look for these conservation principles because they are very fundamental. So I'm going to stop there because these other guys are not in your exam. Actually, yeah, this is in your exam, so I need to say. Okay, so in linear impulse momentum, when I said this before, changes in time indicate that impulse is important, so you have to do it. Or if you have changes in velocity, and then if you have coefficients of restitution, of course, then we have to be careful because these are vectors also, We need to look for vectors. And then in this guy, if we're asked about angular momentum, again, we look at this. And if there are internal motions, right, we look to use angular momentum. So when you study, try to synthesize the concept. And you do that by, again, reading from the book, writing the equations, and writing the discussion, and extracting all the information from those discussions. Okay, are there any questions? All right, so then let's go to, again, I can send you this if you want, or you can construct it yourself. When I was studying for exams, I was always taking one piece of paper, one page, and then summarizing everything. But it's not like an equation. It's not really writing the equations to know the equations. It's what is leading to those equations and what are the implications. What do those equations mean and how to use them. All right. So vibrations. Now vibrations are going to be in a way quite different to what we've done so far. And the reason for it is that vibrations are oscillatory in nature. And oscillatory means that things are changing, things are moving in time, but they are moving in kind of a predictable way. Or, yeah, predictable for sure, right? Because then we can write the equations and predict what's happening. But in a repetitive way, things repeat over time. This is what vibrations are, some oscillations, oscillatory nature. Now, before, when we were looking at kinematics, we were taking pictures of only one instant. In vibrations, we're going to have to think about how is this repetitive motion happening. So we're going to have to visualize motion over time that is repetitive, not only a picture of a certain type of motion. That's what vibrations are. So if we have to look at how something is changing in time, when we're solving our equations, we're going to be able to write these quantities as a function of time. And typically what we want is to know the position of our particles, right? So we're going to have to get now time-varying functions. That is going to be our answer. It's not going to be a number, or it's not going to be just a quantity. It's going to be a quantity as a function of time. And then in our cases, positions are going to be dictated by a spatial variable, x, y, z, something like that, or an angular variable, typically theta or phi or an angle, right? Now, how do we solve problems? So problems now are going to be are going to be similar to what we were doing in the sense that we're going to get an expression for a quantity, but we're going to have to find something that is called equations of motion. And the equations of motion are essentially a set of rules that are prescribing where our particle is in time. That is what the equations of motion are. Now, what are the rules that dictate motion in our life? Newton's second, exactly. So equations of motion come from Newton's second in mechanics. All right? That's good because we know Newton's second law already. It's not a new thing. It's just another embodiment of Newton's second law. Those are the rules that things have to follow when they move. So when we look at a particle like this, a block, we treat it as a particle. What is going to give it its oscillatory nature? Well, the fact that we connect it to a spring gives it oscillatory nature. And we are kind of familiar that you extend a spring and you release it, it oscillates. Now, it doesn't oscillate in whatever way it wants. It oscillates in a particular way that is dictated by something that is called a differential equation, second order differential equation. So don't learn again how to solve this equation. Just remember how you solve it in your differential equation course. It's the same. Of course, now we have here MCK, that means mass, damping coefficient that I'm going to introduce later, and stiffness of the spring. And maybe in differential equations, it was A, B, and C, but it's the same equation, the same type of solution procedure, nothing different. And we're going to define two ways in which we solve this equation. One, where there is no external force applied to our system. And we're going to call that the free response. Does anybody remember how this type of equation, when you had a zero on the right-hand side, was called in differential equations? The homogeneous equation, exactly. Now, the homogeneous equation mathematically means no term on the right-hand side in a very simple way. Physically, it means that it's the natural behavior of the system. Everything that happens is happening because the system wants to behave in that way. That is what the free response is. And then we're going to find also something that is going to call the forced response. How was that called in mathematics? Or the, we had the homogeneous solution and we had the particular solution, right? Or complementary solution, right? So we're going to call that the forced response. And the particular solution means that it's a particular behavior that is dictated by an external entity to our system, which in our mechanics is going to be a force or a moment, all right? But you have all the mathematics that you need. please, again, learn mathematics. It's a language that really allows you to do hard things, and don't learn them every time they are presented to you, because it's the same. When you do circuits, anybody's doing circuits now? You're solving this equation, right? RCL, the same story. It's just that K is inductance, C is resistance, and M is capacitance. It's the same. Now, if you learn it in circuits, don't learn again how to solve it. Just see the terms for what they are and interpret what they mean. And the nice thing is that we're going to be able to do this also for rigid bodies. And we're going to be able to get equations of motion for rigid bodies also. Okay, this class is about getting equations of motion. That's the lecture material that we're going to learn. And as I said, we don't need to do anything else. That the rules that dictate motion are nothing else than Newton's second law. And we know that Newton's second law, when we have a particle, it's only this bit, and when we have a rigid body, we need also the rotational part, which is dictated by Euler's equation. So we don't need to do anything else. They are derived from what we know already. If we have a particle, just Newton's law in its purest form, and if we have a rigid body, we need to include the rotation, all right? That's it. That's really it for this. Now, let's see how we apply that. Let's see. Oh, all right, sorry. We need to first do a few things, sorry. So I think we're familiar with what springs are, most of us, hopefully. Now, you see, these problems and getting the equation of motion, we're going to get it from Newton's second law. And to get Newton's second law, we were doing free body diagrams, right? To see which forces are acting on our system. Now, when we have a spring, the spring imposes a force. And it doesn't really matter, we have to kind of think about it. It doesn't matter if, because this is oscillatory motion, it doesn't matter if the spring is extending or contracting. What we need to do is to be consistent in the way that we write our equation. What I mean for that is, I'm going to show this in a minute, is that we're going to have to take our system, write a free body diagram, or start a free body diagram and say, okay, I'm going to, and this is a choice, not an assumption, I'm going to choose to write my equations thinking about my spring either in tension or in compression. So I'm going to choose that. Now, if this spring, I choose it to be in tension, in which direction is the force pointing? Left or right? The spring is, if I choose it to be in tension, where is the spring force pointing? It's pointing to the left, right? So if I choose that, then I'm going to draw my force like that, and then in my equations, my spring force is going to be positive or negative according to the coordinate that I have there. Negative, right? So that is the important thing. And this free body diagram is going to be valid for all positions, because in my equations, if I am consistent with the choice that I have on my free body diagram, if this spring is now moving in this direction and is compressed, in my time dependence, the force is going to switch signs. We're going to see this, how this works. For a dashpot, dashpots, I don't know if you're so familiar with it, but dashpots are a way to capture this, something that is viscous, something that is dissipative. It dissipates energy. This is going to be our resistance, our dissipative term. And it works in the same way as our spring, we are going to say, okay, let me say that I move my mass to the right, so the dashpot force is opposing motion. It's going to be to the left. Now, we need to learn the definitions of what that force is. Well, the dashpot force is going to be proportional. It's going to be proportional, not proportional. It's going to be equal to C, which is called the damping coefficient, times the velocity, or the velocity times the speed of the particle, which we write here as x dot. Okay? So let me show you how this works on a problem. This is the first example. Hey, do you have any questions so far? No? Okay, let's see how this works, and then maybe questions will arise. So we have a system which is the simple system mass spring damper system. We refer to this as mass spring damper system. We have a block of mass m that is supported by a spring of constant k and is connected to a dashpot of damping coefficient of c value. And there is a vertical force that is pushing up. Let x describe the motion of the particle. So x is going to be our coordinate. It's going to be telling us where the particle is at every moment in time. Find equations of motions, the rule that is going to tell us where x is. This is a kinetics problem in its heart, because we need Newton's second law to solve it. So we do a free body diagram. Now, a mass is going to be, the mass is going to be our system. How many masses do we have? Springs are not a rigid body or a particle, and dashpots are not rigid bodies or particles. Okay, they provide forces, but they don't have mass. And we know that motion is dictated by what happens with a mass. Forces equals to mass times acceleration. So we have only one body, so we look at the forces in this body. So what we're going to do is to know how to draw these forces. I'm always doing this. I'm saying, okay, let this be the equilibrium position of my system. What happens if I move it a little bit in the positive direction? So I'm displacing it, and I'm making it be right here. So of course the spring is going to be elongated up until there, and the dashpot is going to be elongated up until there. Now notice that I'm using x positive downwards. This is okay. I just need to be consistent with my choices. And I do it out of simplicity. You'll see why. So if I say that in the moment that I write my free body diagram, the mass is displacing such that it stretches the spring and the dashpot, where are the forces pointing towards? Up or down? Up, right? So then we have the spring force up, and the spring force is kx, and we have the dashpot force up, c times x dot, and then we have the external load, f of t. Notice that now we're going to have forces that are time dependent, and weight. Never forget the weight. All right? Okay, so we need to write equations of motion. We derive them from Newton's second law. So we go and do what we know. Newton's second law, in my x direction, now it shows x to be downwards. It doesn't make sense with what we were doing before. We're using y, but it doesn't matter. It's just a coordinate. The name means nothing. Now, acceleration is the second derivative of position. Nothing has changed. We're going to write it in that way. Okay, so now let's write the equation of motion. I have summation of forces in X. I have negative Cx dot negative Kx. Maybe I should write this in this way. Negative forcing term. Sorry about that. Negative forcing term. Positive weight, it's equals to 0. And then I'm going to do what we were doing in mathematics, everything that has to do with the system, with the variable that describes the system, which is in this case the position, x, the coordinate x. I'm going to keep on the left-hand side, and everything that is external I'm going to keep on the right-hand side. So first I move my force. Oh, not 0. What am I doing? Yeah, thanks. Thanks for being aware. We're missing the acceleration. Now, everything that is from the system in the left-hand side, everything that is not on the right-hand side. So there should be a negative sign here because that force is up. And then I will just finish it by saying, okay, I really want to be consistent here and show you this is going to be your equation of motion. Now we are not solving it, we're just finding it, stating it. This is the rule that dictates what x is for all times when we solve the differential equation. All right, does it make sense? Yes? This is okay? So we move forward. All right, so this is the simplest example. Now notice that this mg is a constant term. It is only telling you where the equilibrium position is, right? What is equilibrium? You get equilibrium if you say, when is my x equals to 0? So the forces are 0 when equilibrium means that there is no motion, so no acceleration, no velocity, no external force, otherwise you don't have equilibrium. And then you get that x is equals to mg over k. That is the equilibrium position. That is the 0 of your system. When x is that, of this particular system. Okay, let's do this problem. So this one has a little bit more to it. You know, there is a bar and there is a disc. There is a disc that is moving, rolling without slip on a horizontal surface. There is a spring that is connected to that disc. And there is a block on top of the disc, but it's also on a no-slip condition over here. And that block is also connected to another spring, a second spring. Now, we're told here explicitly that the spring is at equilibrium when x is at 0. And we're told that x is telling us where the position of this, the center of the disk is, of that point O. And we're asked to find equations of motion. So now, first question, how many bodies are here in this problem? two bodies, right? We have a disk and a block, two bodies, right? Two things with mass. So this time we have to break up the system, right? Because we are using Newton's second law and Euler's equation. Now, one thing that's going to be important now is choose the positive direction. So you saw in my previous example, I choose downwards to be positive, out of convenience. In this case, we are going to make choices, and this is particularly important for angles. We're going to make the choice of the angular quantity to simplify our lives. Okay, so let's begin by doing our first step. That is going to be, we have our coordinate there, and we're going to displace our first body. And we want to displace it to the right, just because I like tension. So if I look at my disk, I'm going to have how many forces acting on this disk? Okay, let's do the spring force. Is it going to be to the left or to the right? To the left, right, under this choice. What other forces are there? We have weight. We have a normal force. What else? Two frictions, exactly. So let's say that friction is going to be, so if we move that to the right, then friction, let's say that is this way. And then let's say that this friction needs to be this way. And then there is a normal force with the block. Right? Did you get all the forces? So this, in here, we need to get all the forces. This is the big step. Am I missing anything? I think we have everything. Now let's do the block. What do I have here? Ah, okay, let me talk about this in a second. So the block is going to have the spring. So if I said that I was displacing the disk to the right, what is the block doing? It's compressing the spring somehow. So it's natural to make this choice, that this is going to be, so let's call this one 1 and let's call this one 2, spring force 2. Now we have a normal force here, we have a normal force here, and the friction needs to be equal and opposite. And we have weight. Okay, so we have to take care about these two spring forces. Now the spring force F1, about these spring forces. Fs1 is going to be equals to kx, but I don't know what this is. This x? It's not x, right? Not necessarily. So we need a second. We need a second coordinate. We need a second coordinate, and I'm going to say that this coordinate is going to be positive in this direction. So then Fs2, actually, let me do it like this, just because I don't want to confuse it. So then Fs2 is going to be K, Y. Now, we're going to use the signs in the equation. These are just the magnitudes of the forces. So, for the disk, actually, for that disk, well, we don't need the y direction, right? It's not moving up and down. So I'm just going to do the rotation and the x motion. I already kind of revealed the choice of where I want to take my moments. Why do I want to take my moments about point O? Because, I don't know, we could do it about point C if we wanted to, but let's do it about point O. So, what do we get? About point O we have this friction that is going to be, okay, so now this. Now I'm going to choose positive to be clockwise. The reason for it is that my x coordinate is positive pointing to the right, and it makes life easier. You will see from the kinematics that the angle is positive, kind of following the direction of where my x arrow is. So that's why I'm going to make that choice. So this is the choice, and this moment from the friction force 1 times r is positive. This moment from the friction force times r2 is also positive, and this should be equal to the moment of inertia about O times the angular acceleration, which is theta double dot. Now the forces in x, we have negative kx, we have negative friction force 1, we have positive friction force 2, and this needs to be equals to the mass times x double dot. Those are implied there, all right? Now, for the block is just a particle, so we only have one. So we have, in x, we have positive ky. Okay, actually, I chose positive in this direction. So, positive ky, so then kx is negative, and the friction force 2 will be positive, and this is going to be equal times mass times y double dot. Third equation. Now we have three equations, but how many unknowns do we have? We have one unknown, two unknowns, three unknowns, 4 and 5 unknowns. We need some kinematics to work the problem out. Now this is where the choices that I made are going to pay off. Because first thing is that x is related to theta, right? X is related to theta. We can say that x is equals to what with respect to this angle? Is the sector. So x is going to be equals to r times theta. We can get this by using instant centers, by saying that x dot is equals to r times theta dot, right? And if we integrate, we get x equals to r theta, right? You can always do that. Now this is even better for y, because we know that this point that is there connected to the block, or in touching the block, needs to have the same speed as the block, right? No slip condition. So then we use instant centers once more, and then we say y dot is equals to theta dot times 2r. And this gives us what y is. from this, we can get that y double dot is equals to 2x double dot. And we have our fifth equation, and our fourth equation was this. So what is the big deal here? The big part is, let's replace now all of these into the equation that is allowing us to find the friction force first, such that we can go and get our equation of motion in terms of x. Okay, I'm 2 minutes already over, so I'm going to let you guys do it, but that's the big part. Now it's just about replacing. So the big concept here is that even if you have several bodies there, the rules, the equations of motion of one of those coordinates dictates what the other coordinates are doing, right? If I have x, I have y via this equation. And if I have x, I have what theta is via that equation. Does that make sense? So that's why I only need one coordinate to dictate what's happening with everything. Okay, have a good weekend, everyone.